The day the sky fell. How we discovered the rock that ended the dinosaurs. If I asked you to name a single moment in natural history, what comes to mind first? Go on, take a second. Was it that day, around 66 million years ago, when a giant space rock slammed into Earth and ended the reign of the dinosaurs? For most of us, that's the story. A cosmic collision, fire raining from the sky, a bad day to be a T-Rex. But that tidy explanation, the meteor that doomed the dinosaurs, is surprisingly new. If you'd asked scientists before 1980, you'd have heard a very different set of answers. Some thought volcanic eruptions choked the skies, others blamed climate collapse, poisoned plants, or even gluttonous caterpillars that ate all the vegetation. One scientist suggested dinosaurs simply stopped mating. A strange way for the greatest creatures on Earth to go out. But hey, people were guessing. So how did we go from hungry bugs and shy dinosaurs to one of the most famous stories in all of science? An asteroid apocalypse that reshaped life itself. That journey starts with a thin line of clay and ends far beyond our planet, deep in the outer solar system. The vanishing. Long before the mystery was solved, scientists were haunted by a question. How could creatures that dominated the planet for almost 200 million years vanish so suddenly? In the rock record, their fossils are everywhere, until they're not. At a layer that marks the end of the Cretaceous period, the dinosaur record simply stops. Something catastrophic had happened. But what could wipe out not just the dinosaurs, but almost 3/4 of all species on Earth? During the 19th and 20th centuries, researchers put forward every theory they could think of. Volcanoes belching poisonous gases, shifting sea levels drowning ecosystems, global pandemics, even cosmic radiation from a nearby exploding star. Each idea had its own logic, but none could explain everything. The suddenness, the scale, the global reach. And then, in 1980, a pair of scientists stumbled across something that would change everything. The dust of iridium. In the mountains of northern Italy, geologist Walter Alvarez was studying ancient limestone, searching for clues about continental drift. At one site, the rocks showed a perfect transition between the last Cretaceous layers and the earliest Paleogene ones, the exact moment when the dinosaurs vanished. He noticed that the boundary was marked by an unusually thin layer of reddish clay. Curious about what made it different, Walter sent samples to his father, Luis Alvarez, a Nobel-winning physicist known for his inventive approach to problems. Together, they measured the concentration of trace elements and discovered something shocking. The clay contained iridium, a metal almost never found in Earth's crust, but common in asteroids and meteorites. And not just a little bit. There was about 20 times more iridium than normal. When similar spikes were later discovered in rocks from Denmark, Spain, and New Zealand, the pattern was undeniable. This was a global layer, marking a planet-wide event. The Alvarezes proposed a bold idea. 66 million years ago, Earth had been struck by an enormous asteroid. The impact hurled dust and molten rock high into the atmosphere, spreading a fine layer of iridium-rich debris across the entire planet. It was a dramatic claim, and not everyone was on board. Skeptics argued that volcanic eruptions could also release iridium. Others insisted that an asteroid large enough to wipe out the dinosaurs would have left a massive crater, and none was known. Still, the idea had something most previous theories lacked: measurable, physical evidence. The hunt was on, searching for a smoking gun. Throughout the 1980s, teams of geologists scoured the world for more clues. They found shocked quartz, tiny crystals that can form only under immense pressure, the kind generated by a nuclear explosion or an asteroid impact. They found tektites, glass droplets of rock that had been melted and hurled through the air before raining back down. Both were discovered in the same layers that held the iridium. But still, the missing piece was the crater. Then, in 1991, a team studying gravity anomalies off the coast of Mexico's Yucatan Peninsula found something extraordinary. A vast, circular structure buried beneath the surface, about 180 kilometers across. It was named the Chicxulub crater, after a nearby town. When its age was measured, around 66 million years, it matched perfectly with the extinction boundary. At last, the evidence aligned. Iridium dust, shocked minerals, molten glass, and now the enormous wound left by the impact itself. The asteroid hypothesis had gone from fringe idea to front-page science. A world transformed. So what actually happened that day? Imagine an asteroid around 10 kilometers wide, roughly the size of Mount Everest, barreling toward Earth at over 20 kilometers per second. When it struck, it released energy equivalent to billions of nuclear bombs. In the first seconds, bedrock vaporized. A fireball brighter than the sun rose over the Gulf of Mexico. Shockwaves raced across continents. Within minutes, tsunamis hundreds of meters high slammed into coastlines. Debris rained from the sky, setting global forests ablaze. Sulfur and dust choked the atmosphere, plunging the world into darkness for months or years. Photosynthesis halted. Food chains collapsed. The age of reptiles ended. But in that darkness, the seeds of the next age, of mammals, were sown. The survivors, small and adaptable, inherited a transformed planet, building a scientific consensus. Even after the crater's discovery, debate continued. Some scientists argued that enormous volcanic eruptions in India, the Deccan Traps, might have played a major role. Others suggested a 1-2 punch, volcanoes stressing the climate, followed by the final asteroid blow. To settle the issue, an international team of 41 experts from across disciplines reviewed every shred of data. In 2010, they published their findings. The evidence overwhelmingly supported the asteroid impact as the primary cause of the mass extinction. It was a rare scientific consensus, and a landmark moment in understanding Earth's history. But even then, the story wasn't finished, because buried fossils were about to give us a front-row seat to the apocalypse itself. The day it happened. In 2019, paleontologists working in North Dakota revealed a site called Tanis. The discovery had been kept secret for years, and when details finally emerged, they stunned the scientific world. Tanis captured the immediate aftermath of the impact. Fossil fish were found with tiny glass beads, molten droplets from the explosion, lodged in their gills, as if they had suffocated while the debris was still falling. A turtle was discovered impaled on a tree branch, likely thrown there by a massive wave triggered by the impact's seismic shock. Even a small dinosaur leg, possibly belonging to a Chicxulub, was found, seemingly torn from its body by violent currents. By analyzing growth rings in fish bones, scientists realized the animals had recently spawned, suggesting the asteroid struck during springtime in the northern hemisphere. For the first time, we weren't just reading about the extinction. We were witnessing its exact day, preserved in stone. A visitor from the outer solar system. Despite all this progress, one mystery remained unsolved. Where did the killer asteroid come from? In 2024, researchers analyzing another rare metal, ruthenium, found the answer. Ruthenium exists in slightly different forms depending on where an asteroid formed in the solar system. By comparing the KPG boundary's ruthenium signature with samples from other ancient impacts, scientists could trace its cosmic birthplace. The result was unexpected. The Chicxulub impactor wasn't an ordinary inner solar system rock. It was a carbonaceous chondrite, a carbon-rich relic from the outer solar system far beyond Jupiter. These ancient bodies make up less than 5% of the meteorites that fall to Earth. They're time capsules from the dawn of the solar system, containing the ingredients that built planets, and possibly even life itself. In other words, the rock that ended the dinosaurs' world began its journey billions of miles away in the cold, dark reaches of space. Conclusion. So, after 66 million years, the pieces of the puzzle finally fit. We know when it struck. We know where it hit, and now we even know where it came from. A rare wanderer from the edges of our solar system collided with Earth and changed everything, wiping out the giants that once ruled the land and clearing the stage for mammals, primates, and eventually, us. It's more than a story about extinction. It's a story about discovery, about how science moves, step by step, layer by layer, from mystery to understanding, from a thin line of iridium in a rock to a revelation written across the stars. The day the sky fell wasn't just the end of an era. It was the beginning of the world we live in today. If you love journeys through deep time and cosmic coincidence, don't forget to like, subscribe, and keep exploring. Because every rock, every fossil, every atom of metal hidden in ancient clay has a story to tell.